Over here you see the energy levels of electrons in an atom. The first shell that's very close to the nucleus can hold a maximum of 2 electrons in one 1s orbital, and the second shell holds a maximum of 8 electrons in one of the 2s shell and 3 times of the 2p shell. And the third shell holds a maximum of 18 electrons in 1 times 3s orbital, 3 times of the p orbital, and 5 times of the 3d orbital. And that's how it explains the arrangement of the periodic table. Why the first row we only have 2 elements, because the first quantum shell can accommodate only 2 electrons. So in terms of electronic shell, a group of the atom's electrons within the same principal quantum number 1, quantum number 2, quantum number 3. So in the second shell, it contains 4 orbitals. In the third quantum shell, it contains how many? Yeah, you got it. 8 orbitals. That can house a total of 18 electrons. Now for the p orbital, each of these 3 are mutually perpendicular. So in a 3-dimensional manner, x-axis, y-axis, and z-axis, they are all identical in shape, dumbbell shape with 2 lobes separated by a node. A node here in chemistry and science means it is a region of 0 electron density. It means virtually you can find no electrons at the particular zone. So you may ask, how does electrons go from one side of the orbital to the other? They just jump, they skip, they teleport. Now why do we have 2 colors for p orbital lobes? We know that orbitals can be expressed in the mathematical wave function. So you know the wave give off graph 3D functions. So it's being represented by the algebraic sign plus and minus. Now you also have to know what does it mean by ground state electronic configuration. It just tells us the most stable, the lowest energy electronic configuration of an atom. There are 3 rules of electronic configuration you have to know. Number 1 is the alpha principle. That means that we should fill in from the lowest energy orbital first, all the way down to 1s, then 2s, then 2p, then 3s, and then 3p, then 4s, and 3d. We cannot say, okay, I feel like putting it at the 2p first in place of 1s. No, not going to happen. The second rule is a Pauli's exclusion principle. It tells us that electron spin can only have 2 orientations, one up, one down, right? And the 2 electrons can occupy in the orbital, but they must be of opposite spin. So in the orbital, recall, it can house a maximum of 2 electrons. The 2 electrons cannot face the same side. It doesn't happen that way. It must be oppositely spin. Okay, and then they can pair together. And the third rule is a Hund's rule. It tells us that if 2 or more empty orbitals of equal energy are available, electrons occupy each orbital with parallel spins until all orbitals have 1 electron. That's such a mouthful. So to make it simple, just imagine you go to a bus, double-decker bus, you go up the staircase, and then you see, oh, there's chairs, there's partition in pairs. You always go with the one without strangers first, right, and sit alone, than to go and sit with some strangers, even though there are many empty chairs about. That's not very normal, but doesn't mean you're odd. So you see here, this is clearly expressed by the carbon electronic configuration. Now why are these 2 electrons not paired? Because the Hund's rule says that the first electron goes in here, the 2p orbital, then the next electron it can come here, right? But the Hund's rule says no, it's got to be in the empty orbital first. Try not to pair them up until you have no choice. Like in phosphorus, no choice, you have to pair all of them up, right? Then you fill into the next orbital by the above rule. And for phosphorus, what do you see? All these electrons are not paired. So the next electron will be paired. You have no choice. But in this case, if you have a chance not to pair them together in the same orbital, you do it following Hund's rule. Why do atoms form bond? Because remember, all chemical reactions are driven towards stability. So when they bond, they become more stable, they lower their energy. So energy is released when you form bond. How do you remember? Now when I want to break something, I want to break a bond. Let's say there's a piece of paper here, I want to break it, right? I need energy. You hear the sound? One more time. So this energy that I commit to breaking or tearing the piece of paper is being channeled into sound. And also, you see the atoms here broken apart. So I just broke some atoms, many atoms in fact. If you break a bond, you use energy. So if you form a bond, it is the opposite. You release energy. And when you release energy, you become more stable, right? When you're hyperactive, you have so much energy, you move around like a wild kid, and then you get tired at the end of the day. You sit down and rest. Low energy makes you sedative, makes you stable, inactive. Very good. Valence electron means the outermost shell of an atom. Highest energy, outermost shell, furthest away from the nucleus. And there are 8 electrons in the valence shell, so that's why we have the term called octet, oct8. Reactivity of an element is being governed by how readily it can take on the nearest noble gas configuration. And that's why some elements prefer to be negatively charged ions, like fluorine become fluoride, you don't see a F+. Or sodium prefers to form Na+, because it's easier for them to lose electron to have a electronic configuration that's the same as a noble gas. Ionic compound. So ionic compound is just defined by the formation of a bond via the transfer of electrons. You form charged particles, cations and anions. Covalent bond compounds just denote by the sharing of electrons. They don't transfer, but they share together. It's like holding hands, sharing. So these are some structures that you have to be familiar with, and got to translate between electron dot structure, we call it Lewis structure in some schools and countries, places, and translate to line bond structure. Very easy. Each line represents a pair of electrons, 2 electrons here. So you can translate between the hydrogen and the carbon connected by 2 electrons. Why different color? Because each of them contribute and share 1 electron. So you get a pair of electrons holding hands here, the line. The same goes for ammonia. These 2 electrons are in blue. They come from nitrogen, group 5. So we have 2 electrons that's not used for bonding, and we call them lone pair, and we depict here in the structure. Similarly for oxygen, the lone pair are denoted in pink, not bonding. We also call this line bond structure as a Kekulé structures to commemorate the celebration of the discovery of the benzene structures, one of the critical molecules in the 20th century. Now the number of covalent bonds that each element forms depends on the additional valence electrons needed to reach noble gas configuration. Basically, if you look at the periodic table from period 2, you can think of it as group 1 forms 1 bond, group 2 forms 2 bonds, group 3 forms 3 bonds, group 4 forms 4 bonds, group 5 forms 3 bonds or 5 bonds, group 6 forms 2 bonds, group 7 forms 1 bond. So 1, 2, 3, 4, 3, 2, 1. If you can imagine this way, that'd be great. So this is group 1, 1 bond, group 4 forms 4 bonds, group 5, 4, 3, 2, 1. So 3 bonds, 2 bonds, and 1 bond, because they only need that number of electrons to have a noble gas configuration.